Welcome back to Cloud Computing and Big Data, Parallel and Scalable Machine Learning and Deep Learning. Today we have our lecture 2 about machine learning models in clouds. And the lecture will take us firstly really to a moderate introduction to machine learning. So it's basically an example where you don't have to have any prerequisites. You can understand machine learning from the ground up, if you want. We're using one of the most simplest and earliest learning models in machine learning called the perceptron learning algorithm. So this would be an interesting material for those of you who have been not using machine learning in the past. And once we have done this, we will also look a little bit more, of course, how we can do this in cloud computing environments. Also there we start with a relatively low learning curve. Thinking about using the Google Collaboratory that you can do yourself also in the cloud very easily before we then thinking about HD Insight clusters in MS Azure, for example. So interesting lecture, hopefully, for all of you that still need to learn a little bit about machine learning. But before we dive into the material of this lecture, let us review what we had the last time. And lecture 1 was really another introduction lecture. We looked at cloud computing and the topic of big data, again, from quite some perspective as a broad overview, but still we're able to clarify numerous different terminologies, which was one of the parts in the foundations to understand really what cloud computing entails. And we have seen that here in the foundations, you have the ingredients of this interesting scalable and elastic cloud you see, which stands a little bit for cloud computing, which still consists of nothing else we know from computing, like hardware, storage, server software, but also the network, the interconnect between the different servers. And one key term, however, we already formulated in lecture 1 was really services. You remember we introduced a little bit already the infrastructure as a service, the platform as a service, and also the software as a service ideas, basically on different levels of computing and software and so on. And for each of those, we will have, of course, a lecture later on in our course. But we already have seen that the name service is very a central term here in the cloud computing course. And this is often the idea that users can have, some service request to this cloud, and in a way, very abstract manner, you have to pay for the services, of course, with pay as you go and subscriptions. We will talk about this also in later parts in the course. But then you get a service that is quite virtualized somewhere, so you don't know really where it's happening. It's somewhere maybe in an Amazon cloud, somewhere in the US or in Europe. And the key message to take away is that it's really abstracting from the needs a way to have your own server sometimes, right, in your own cellar. And we have also motivated a little bit why this can be further useful, because laptops usually see basically lots of limits, not only in terms of computing itself, also the memory that laptops or desktop computers maybe even have is not sufficient. So you would extend your computing capabilities by using famous cloud vendors like Amazon Web Services. In the course, we also will use MS Azure, for example, but also the Google Cloud. But thinking then on these different models of the idea of infrastructure as a service, platform as a service, but most likely also software as a service, you all know you have used that, right? So Google, with all the different Google Docs, is nothing else than a perfect software as a service example. And we have seen there sometimes also very specific ones, like the Uber Cloud for engineers, for example, or EOSC, if you want here, the European Open Science Cloud, which is quite optimized for the needs of research and academics. So hence, many of us use services in these different clouds, let it be Google Docs, or even the service character is a little bit hidden. It's just a sort of profile social network idea that we of course know from YouTube, but more likely also from Facebook, etc. So with this, we also motivated a little bit the fact that in a way, big data is real. If you think about how many users Facebook alone now has, or how you really deal with large quantities of data in the different clouds, we know that big data is real, and we have also learned a little bit in the first lecture that this might be not only about the volume, as this graphic here suggests. It could be also quite the velocity, for example, right? We motivated here the fact that there are lots of tape archives. They can take lots of petabytes. So that's not a problem of what 1 petabyte stored. However, the problem comes as the velocity comes in with 20 seconds, right? So 1 petabyte every 20 seconds is a problem. So this means the storage archives will quickly run full, and then this means enormous costs. So we have to deal with this, and there are different ways how to deal with it in cloud computing. And one example of a cloud we have seen a little bit in terms of motivating the initial parts of it, really relatively low level still, you would say, here's this elastic computing cloud example. You have an Amazon, for instance. It offers users EC2 resources, the elastic computing cloud resources, but also S3 resources, storage resources that we looked in the last time. And it's, of course, very secured. So you would have a sort of firewall, and only specific users can access this cloud. But of course, this is just rented for you somewhere. And still, this whole setup of virtualized resources that we will explore in lecture 4 shows also you can shrink up and shrink down with your needs. And this is quite useful depending on what you need really to perform in terms of applications. We will basically use maybe a very CPU heavy idea. And we talked a little bit about the terminologies in the last course, also about what is a multi-core CPU versus a many-core GPU, just very shortly. The multi-core CPU has just a couple of cores, as the name suggests, multi of them, with a high single thread performance. So cutting-edge CPUs, which have an enormous power, number crunchers with different cache hierarchies, as you see. However, you cannot put more and more of these core on the chip because it will be overheated. Hence, these days, we talk also a lot about GPUs that you see here a little bit, where each of the different, let's say, cores, and there are many cores on them, is just of moderate performance. So it's not really the high core CPU core that you have here. They are actually more, let's say, on a moderate level in terms of performance, but the benefit is you have extremely many of them in the thousands, and you have to fuel essentially the GPU as being an accelerator of sort, always via the CPU main memory to the device memory, and then the GPU will talk about and will basically take this data and talk about applications, whatever applications they are. We talked about in the course will be several ones coming. We start a little bit with big data analytics using Hadoop and Spark, and we clarified the term big data analytics a little bit, contrasting it also a little bit with big data analysis here and there. But it could be also deep learning that we see in later lectures, then in lecture 6, 7, when we talk about GPUs more. So, and then also, of course, about deep learning and cutting edge modeling. However, today, as the name suggests, we do machine learning models in clouds. We will start, as promised, with a very moderate introduction. So from the ground up, it's still helpful, of course, to look that up in much more detail. There are lots of different aspects and facets today that we will, basically just very shortly address, like regularization, cross-validation, hence validation for model selection. There are many topics that a real machine learning course entails that we cannot really focus on, mostly because we want to also learn how it is done in clouds and not just use lots of theory. Hence, we see that a little bit as an application driver here in the course, and also we will extend then this trivial models that we will basically start a little bit with, like the linear perception model and understanding classification and so on, and we'll extend it later also towards deep learning. Hence, the ingredients of this linear perception model and the basics we go through today with training, testing, and so on. This will be also quite something which is still used in deep learning today. So even if this model comes out of the late 50s, we see basically that the general concepts, of course, of machine learning stays the same. Then in the second part, we have an application example, again, that we will use in the Google Collaboratory here. And of course, in MS Azure and HD Insight, you can do similar things because we use Jupyter notebooks. And this will be also alluding to your first assignment. Hence, we injected this lecture as a very practical lecture at the beginning of the course so that you can start with your first assignment, hopefully already next week. So in this sense, it will be a walkthrough character, just having a very simple extension to the linear perceptron model using a concept and learning model called logistic regression. However, I'm aware that many of you don't know even what a learning model is. So hence we dive directly in the machine learning fundamentals. So classification of a machine learning model we do today. We use supervised learning, and supervised is characterized in machine learning with the fact that you have data of this form. So you have some sort of feature vector that explains the data, this red dots here, for example, and also the green dots, but you have also the guiding label Y. In other words, we know for each of this vector, is it a red or actually a green point, right? So this guiding label Y is why we call it supervised. You see that here a little bit, the input is mostly essentially the features that we have in this feature vector. And then of course, the guiding output with a label, as it is called, enables us to really check always when we do a machine learning model. And that's what we will do now in the next couple of slides, to check really as a supervisor, have I done the correct classification, or is a red dot not really a green dot? Hence, this is a very specific area of machine learning. And the feasibility then of machine learning comes a little bit with the idea here we discussed before. So we want to understand a pattern, right? So we have to see that in our applications we have today in the course, there's a sort of ingredient that there should be a pattern. So not a random number generator or something. So it should be a real application. And of course, usually when you have an exact mathematical formula for this, you would just go ahead and implement it. Hence, for machine learning, it makes also sense to attack those problems and applications really, where there's no exact mathematical formula. And of course, the third ingredient, if you want, and prerequisite is really data exists. So we want to learn in this course a little bit with the facet also from big data. Hence, these are the three ingredients that we already discussed. And what we basically see here today also is data science, and we really fuel it with computing and lots of modern techniques. So let us come to a simple application example to motivate machine learning a little bit. So hence the classification of flower is here the question. And you see here some of the flowers of the type Iris setosa, which we consider as one class, similar like this red dots here. This would be one class, and there's another class called Iris virginica. And this would be characterized here as an example by the green ones. Now, the question would be, if you are in the field and you make a photo with your iPhone or whatever, smartphone you have, you would to know what flower is this, and now when I ask the audience, usually I would say, can you distinguish in the photo yourself, what is the Iris setosa or Iris virginica, or in other words, what is this flower? That's a classification question, a binary classification question. Right? Group of data exists, we know that. But the new data that's coming, we want to know in which existing group it is. And this gives us already also the opportunity to show you some systematic modeling a little bit that helps in data mining, helps in machine learning. We want to understand first the business, what we are doing, the application understanding. Hence here, we have a classification of a flower. This is something called the CRISP DM model. That I also give you now in the lecture throughout to get a little bit more structured view how you deal with machine learning problems. And we will also further use this also in the assignments and in other lectures so that you get a little bit of hands-on of experience how you can structure your machine learning projects if you want. So once we have clarified this, the learning problem is really something we call the prediction task. We would say now, okay, we have this new photo. How we predict it. Is it class setosa or virginica? Hence, we call that a two-class classification problem, a binary classification problem. It is admittedly very simple, but captures the essence of supervised learning very nicely, especially for beginners that don't have so much experience in machine learning. So hence, the next step would be, once we have the business understanding, to think a little bit towards the data now, right? So hence, what attributes about the data could help us? Right now we have pictures, okay. It all shows flowers, okay. What flowers have? Usually in terms of features, okay, we have some sort of color that seems to be very similar to the others in all the different classes. Is there something else where we can see maybe some features in the data? And this brings us then to the next step where you say you have to understand your data, right? We say again, data exists. And to check the prerequisites, we can say there seems to be a pattern because people know it's an Iris setosa or Iris virginica. So there is a pattern, and it seems to be, if you're, let's say, a little bit an expert in plants, there's something about the sepal and the petal width of flowers. And this somehow influences the type. So there seems to be a pattern there. We also know that there's no mathematical formula that directly distinguishes, these two flower types. Hence, we're looking at data that really exists, and we're very lucky here in our example. There's a very nice UCI machine learning repository that I also would like to recommend you for those that want to play around a little bit with machine learning, learn the basics. There are lots of interesting machine learning data sets that are also quite nicely, let's say, cleaned and prepared. Here we have a data set with 3 different classes: Iris setosa, Iris vesicola, and Iris virginica. Hence, you see also, I somehow work already on the idea that we will get rid of one of these classes for a very simple reason. It is a more complicated class. And this is a first, let's say, part in the machine learning where you then otherwise get a little bit confused. Hence, we will basically perform some data preparation here later. But we have the understanding that this data collection of the UCI dataset Iris gives us now the sepal lengths in width and petal and width and length, each of them in centimeters, and the corresponding class label, making it a supervised classification problem. Hence, with a certain data understanding that corresponds to the business understanding here in the CRISP DM, we sort of thinking, let's go a bit further. Plotting the data can usually help. And as I said, you see here data preparation. We can say that as a data preparation step here, we sampled 2 classes out of the 3 original ones. Hence, we just have Iris setosa and Iris virginica. And with this, we can start plotting the different data sets that we have. You remember we had 50 samples from one tube and 50 from another, making it all in all 100 samples. Now you see here, if I would just take the features now that we learned and pick 2 of them, the petal width and the petal length, we don't have really the labeled situation yet, right? But you can already see a little bit the pattern we thought of in the terms of length, in the terms of width, right? So there are definitely 2 clusters. And you notice here that I omit a little bit the why, right? There's no label yet in this data. Just to understand it a bit better, when we now use our label data that we have in the supervised learning scenario, then of course we can color it, right? And again, we use the analogy of the green and red data set in a way. But now we have 100 samples, you have a pattern that exists, you understand the data quite well, we prepared it a bit with having just 2 classes. Now, this is not machine learning, right? So this is just data visualization techniques, data understanding, and here and there we have already prepared the data with subsampling, but this is no machine learning. Machine learning and modeling now comes as a next step. And this means we have to do something to think about what model could help to distinguish now a new data point, right? So this is now the new model and the new data set that wants to use a model to understand, is it basically Iris virginica or Iris setosa? We talk about this as some sort of a decision boundary needs to be formed by this machine learning model in this trivial example here of a binary classification problem that, when we have plotted the data item, then we were very sure, okay, this from the size somehow and, from the petal width and petal length seem to be an Iris setosa. It basically then refers to the question now how we can model this decision boundary, right? And this would be a machine learning model to understand a new future data item. This new picture that you took has also certain sepal width and, length. So in this sense, we can have the separating line a little bit, let's say for mathematical convenience, easier modeled. If some of you remember, here's a linear combination, essentially saying, just as we just discussed, when we have a line and we model this in the space, we can of course now shift this line. And this says a little bit about this, WI, which would be a very important part in the course throughout. The weight, because the red one is something what we want to learn, right? And the X is a constant. That's of course a data set, right? Our features that we have in the data. And here we say for convenience, we would say +1 is everything which is an irisogenica and -1 is everything which is an irisitosa. Hence, we talk about a certain sign function here, depending of if basically the threshold is bigger or lower the threshold. In a compact notation, you would say we just take the sign from it and define the sign like this. So that's where modeling starts. We have somehow a linear learning model, right? We see that here. The weights and everything is still in the linear regime, and hence it's a sort of more trivial problem, but already for people that are not so inclined with machine learning, they are now starting to think, okay, how this comes all together. And for this idea of a linear learning model, we need a certain machine learning model that helps us. And this is actually something which have been developed by Rosenblatt, as you see here at the end of the 50s, actually modeling basically the perceptron after neuron from a human, right? So as you know, neurons are very interconnected. They have different, activation functions in a neuron to actually have repeated stimulus and then transfer the stimulus further in the neurons and so on. But let's not move too much to neuroscience. So we stay with the modeling. And the perceptron learning model is a little bit characterized like this. You have these different features that now go in to this so-called perceptron, which are our features in the data set, right, that we have here. And for each of those, you see here essentially the idea to introducing weights for them. And the weights needs to be learned, except also, of course, the threshold needs to be learned as well, that we model here as a bias in this particular perceptron learning model. And then there's a certain activation function that tell us now the label. And in our example, again, we do this sign function here with +1 or -1. But of course, we can also play with this, as we see later when we go towards regression techniques and so forth. But this is a general idea. Depending on the dimensions, you have the input data. These are constants. The label is a constant we learn from in our data set. But the W's are now the interesting things that we want to learn. This is machine learning, what we basically set out to do. Hence, we have lots of training data. For mathematical convenience, we put the threshold also as a learnable parameter. And as such, we can essentially do this on a much more compact notation. But as we see here as a just kind of evaluation example, right, that you see the modeling has been done. It's a perceptron learning model. And let's assume we have trained it. We don't know how to train it yet. That will be coming after this, just to show you that essentially this learning model would work. If you put now in these different numbers and assuming we would have weight that we learned, and then the bias would be 0.4, and you have a very trivial example here, you will see that when you put in this data sets completely, it will be actually always returning the right results, +1 or -1, actually like the label here, right? So it is possible that this simple model then actually enables us to come to the right conclusions with the labels. So that's what we want. And this was already an evaluation of a model we actually, let's say, were given as a trained perceptron model. Now the question arrives, what would the training phase will be, right? So how we train such a model, because the weights have been now just friendly given to us, but we want to, of course, understand how we can train them in reality. And this brings us to the next idea of saying that, the kind of learning model should play with the line, right? So with the 0.3 we've seen before and the bias 0.4, we had a fixed line, right? It was sort of fixed somewhere standing with a linear combination using weights here. We have a fixed line. However, when you now think of adjusting this weight and the threshold, a little bit from basic mathematics, I hope, but we shift this line around. And this could even mean that we sometimes cross points, which then, of course, actually have their decision space changed, which are standing here for the color. You have green and blue as an example. So where then the class label should change. Hence, and this brings in a little bit the hypothesis idea here, h of our x data points is essentially the sign function by playing around with the weights until it's actually fits, hopefully, the guiding label y as much as possible. But how this line exactly looks like is actually part of a big set. H, right? So the hypothesis set could be anything. Could be, lots of different values from this weight. So this is a huge space, and we're searching in this space to find really this hypothesis that really make it work with the guiding Ys. So this brings us more about the idea of the modeling. Okay, we have to play with the Ws. So how we do this. Before we, however, go to a concrete learning algorithm that we now need, that actually was also implemented from Rosenblatt and suggested in the end of 1958 here, where then we talk about the perceptual learning algorithm, and it actually works a little bit simpler when you modify the data a little bit. In a sense, it's just a notation. For some of you from simple mathematics, you know a little bit the dot product notion here of W times X here is the same like W transpose X. That's why you see the weights sometimes getting in a vector form, because then for mathematical convenience, we can actually have a very compact notation. So this is equivalent. The H of X assigned as W transpose X when we also incorporate and define that X0 is V1, right? So this is something where we then want to start with 0 to actually have this bias fit in. Because if you remember, the threshold was also something we want to learn. And this is a equivalent dot product notation, and also very relevant in the course later because we will use it again and again. Coming now to the real algorithm, perceptron learning algorithm, that was basically now put to the perceptron learning model. We would just pick one misclassified point somewhere and would try it out, right? We have the sign function, we have a initially defined weight, and every time we see that you say it's not correct, we actually update the weight vector, right? We say the weight vector with all the W's we have should be always, the weight vector plus. And you see here a little bit, because we have plus and minus 1 for, the guiding label defined, right, from ourselves. We actually come to the conclusion here that it's equivalent of adding or subtracting a vector. So a very, simple idea. That's why I put it here as A and B. Again, just to say that is the update rule that you need to learn, right? So we learn the weights new from the previous learned weights, but also to some modification that hopefully should make the learning better. So, and when all the points are not, not misclassified, then we will stop. But, in many cases, it will be not like this. So we will go many times through this iteration. It's a called iterative method using this label training data. And at some point in time, we hope it will terminate. I brought you a little bit of kind of short visualization here. You see the perceptron visualization converges here. So it plays, as I said, with you adding a vector, subtracting a vector, that actually is then the idea of modifying this line significantly over the time of all the training set examples, and then hopefully converges to this line that actually separates, as you see here, the blue and the red dots. Now, this brings me also the opportunity to say that this was, of course, a very simple idea here of having the two kind of classes only. And we actually have removed the third class, if you remember, because the third class is not linearly separable. And linear separability is a very important factor here, unfortunately, very rarely in practice. Hence, a linear perceptron algorithm here would be not performing very well in many practical problems. Just take that on board. But coming back, what it now meant for us here in learning to obtain the class of new flower, it's a similar principle. Then you see here, essentially, we said in the beginning, we need a sort of decision boundary that should be essentially here, one line in space. And exactly this might be the one, but over time, the algorithm has probably played with a lot of different lines here, right? And to come to this conclusion finally, because it was just picking one after next from these points and was realizing, no, none is misqualified. They are actually minus the threshold or plus the threshold, above or below. And with this, we can terminate, like here, the terminal idea of the algorithm. Now think about that one data item of the red ones would be along here. Then it would not be terminating, because essentially the boundary would be wrong and misclassified. Hence, it will further play with this. And that's why it's so important to have this linear separability, right, in the data. And chances are, if the kind of data item is here, we can still hold a line that is sort of here, maybe over many, many iterations. So it's quite an elaborative algorithm also to always do this. But we will find at some point in time, and this is, I think, guaranteed even in the algorithm, it will converge if the data's linear separability present. However, so what means linear separability? And that is also that it means like when only one of the red ones would be in the regime here of this element. So let's say here where I have now the cursor, or the red dot would be a red point, the data would be not linearly separable. There's no line that can separate them, right? I think that's visible for all of you. So hence the same is true for the green one. If you would have a green item somewhere here above, in the red regime here of this elements in this cluster, there would be no line where you can craft a separability assumption. And with this, the learning model will never stop. It will work. It will take the next misclassified and will probably end up with this one fellow that will be forever misclassified. Hence, there are some adaptations to this algorithm called Pocket and others, but the key message to take away is that, of course, the perceptron will be just a starting point for later neural networks, where we have the same model, but then on steroids by combining this model with many, many, many different of them, calling it a neuron, and then have it in hidden layers and so on, and much more of them. But this would be in future lectures. So let us take stock a little bit of what we learned. So firstly, in terms of terminologies, for those of you that have not used machine learning before. Firstly, machine learning models, right? So we said, okay, there's a perceptron machine learning model, this linear learning model, linear in weights, and that's why it's a linear learning model. So, and we said it's doing the job, but it is missing something. It needs also an algorithm, right? So hence we would say usually there's a machine learning model and you have a machine learning model algorithm with it for optimizing it or learning from it, to be more precise. Right. So in other words, we have the perceptron learning model and we train it with the perceptron learning algorithm, which was very simple, admittedly. The same is actually true when you think about these two ideas, when you go to support vector machines, where you have quadratic programming, or neural networks has the algorithms of backpropagation of error. So they have all the different learning strategies, as machine learning models. We also see the labeled data set idea. Right? We say in sample, that is data given to us. But this is something what we don't really want to optimize on only. We want to be good in learning. In other words, we want to be good out of sample. Whatever new data, and this is the idea of out of sample, right? So this is in sample because this is already labeled and our data set here, as it's also in sample, is also a data set part here. That's why we call it in sample. But our machine learning model should be working well out of sample, right? And this is an important idea of making the machine learning model robust for future data. Not only this part, of course, there should be many other data points, maybe here, wherever, for which we optimize then this machine learning model. You have also seen the idea of the training set and the test set in a way. That we will, take the data and cut it, and then we'll be taking one by one as the algorithm was doing and going through it. And this is something like will be more important also for the next parts, where we can take, of course, this kind of training examples and cut them in different pieces, calling it a training set and a test set. So, and we use the training set normally on a trained system. That's what we will also show you later, and train with it. But this would be then an in sample, so to speak, for us, because we trained on it. So not what we want to have our goals in. Of course, the training will be led by the idea of the samples of the in samples with the labels. But what we want to really have then to achieve good accuracy with the trained set in the test set with data the trained system has never seen before. And this is the idea of being good out of sample, right? To test it with a test set and then achieve equally good performance, although the data is very new. Hence the idea of human analogy with learning, right? We learn something, then we can apply it to many different elements. So these are very important parts in machine learning to understand, right? When you not have understood this yet, then either come to me again in the office hours or maybe look also the lecture again a little bit. Towards the end of the first part, I also want to give a little bit the rise to the idea, basically what would be more other models based on very similar ideas, right? We would still have the idea now of this linear learning model. So we sum them up linearly using weights, the input that we get, and we know it's constants, right, from our data sets. All we need to do is learning those. And once we have this learnable weights, and now the question is, of course, what we do as type of activation function, right? And there are different versions that you can do that are all linear learning models, linear classification, for instance. What we have done, right? We use the sign function for a simplification, +1, -1, to have a two-class problem. And we will extend it later on here in the course or to others. And this is already the learning model we discussed. But we can also thinking about adding, regression to it. And regression is not a fancy word. It's just said more or less real valued output, right? And this is something where you can also have essentially then just the value itself. So basically, you don't need this activation function. You can have the identity function or whatever in this context. But an example also showing you a little bit the idea of deployment in this CRISP-TM model would be now that a TV channel would say, okay, we give marketing money to spend on TV advertising on the specific show. And they're using this in daily practice. And you can use linear regression technique to understand the question of how much sales, should be given actually marketing money to really, having then essentially that the show is really, sold on TV that people are looking at and so on. And this is, of course, with ads the same way. If you have someone having a company, they maybe, do this as a deployment of the model. They use it every day. So the training is almost done. At some point in time, you would maybe come back and then, do another model on it. We talk about this later, basically in part 2 more, that of course you can also have different iterations of this, do maybe different models. What you would say here, because when you come to this modeling step, each of them are different models. Linear classification, different model. Linear regression, different model. And logistic regression, we didn't talk about yet, is also a modeling technique. So here the interesting thing is to start more or less a little bit to non-linearity that you want to capture in the data. You will see that the data in practice is quite, something which requires us to think about much more non-linear ideas in the data than we had before with this beautiful separation and so on. So the logistic function here is then the idea of adding a little bit the idea of a probability from 0 to 1 into it, depending on the, let's say, input value. So you would still, sum up linearly using weights and doing the idea that we just discussed. But then, of course, you would use the so-called logistic function that you see a little bit here to smash them between 0 and 1, as some people would say, depending on the values that you get. However, again, logistic regression is an interesting technique. We look at this also in the second part of the course, again, how we put that now into cloud computing. Of course, it has many different facets, and we will just actually have a couple of them in the second part discussed. So logistic regression is also, which is basically in the pocket of each machine learner and is also substance usually of a machine learning course. And again, encourage you to have a proper machine learning course alongside if you're very interested into these topics. And also here, I brought you a small video that shows you again a little bit the idea of logistic regression, which is quite loaded. It can actually quite achieve good results in practice already, being, let's say, still a relatively simple model. And I think with this, we stop for the first part with a short break and talk to you in the second part.